In late August 2023, something happened that instantly sent shockwaves through the global tech industry. At first, it looked like just another smartphone release. No giant launch event, no dramatic countdown, no massive global marketing campaign, just a quiet announcement from Huawei. But within days, that single phone would trigger panic, confusion, and intense debate across Washington, Silicon Valley, and the semiconductor world. The phone was called the Mate 60 Pro. And according to many experts, it was never supposed to exist. The timing alone immediately raised eyebrows. While the phone was being released in China, US Commerce Secretary Gina Raimondo was visiting Beijing, the same US government that had spent years restricting China's access to advanced chip technology, suddenly found itself facing an uncomfortable question during a diplomatic visit. How did Huawei just release an advanced 5G smartphone? For years, the United States had imposed wave after wave of sanctions designed to cut China off from the most powerful semiconductor technology in the world. The goal was simple: slow China down, especially companies like Huawei, which Washington viewed as both a technological and national security threat. Those restrictions were severe. Huawei lost access to Google services. American companies were blocked from supplying critical components. More importantly, China's access to the world's most advanced chip-making equipment became heavily restricted. And, according to most analysts at the time, those sanctions worked. Many experts believed China's semiconductor industry had effectively hit a wall, a technological ceiling. The common assumption across Western media and tech circles was that Chinese chip makers were stuck years behind global leaders like TSMC and Samsung Electronics. Some believed China would remain trapped at older manufacturing nodes for the foreseeable future. That's why the Mate 60 Pro immediately became such a mystery. People in China began posting speed tests online. Users noticed surprisingly fast performance. Even more shocking, reports suggested the phone was capable of advanced 5G connectivity, something Huawei was supposedly crippled from achieving after years of sanctions. At first, many outside observers assumed there had to be a catch. Maybe Huawei was using old stockpiled chips. Maybe the reports were exaggerated. Maybe the phone wasn't truly advanced at all. But then came the teardown. Tech analysts at Tech Insights opened the phone and examined its internal hardware piece by piece. What they discovered stunned the industry. Inside the Mate 60 Pro was a chip called the Kirin 9000S. And according to the analysis, the chip had reportedly been manufactured by SMIC, China's largest chip maker. That discovery changed everything, because the chip appeared to be built using a manufacturing process far more advanced than what many believed China could achieve under sanctions. Suddenly, the narrative that China had been completely contained technologically started to crack. For years, Western restrictions were designed around one central assumption. If China could not access the world's most advanced semiconductor tools, then China would eventually fall behind permanently. But now, sitting inside a smartphone being sold openly in China was evidence suggesting something very different. China may have found a way forward anyway. And that possibility created immediate anxiety far beyond the smartphone industry itself. In Washington, lawmakers demanded answers. Analysts began questioning whether export controls were actually working. Semiconductor experts across the world started debating the same question at the same time. Did China just quietly break through one of the biggest technological blockades in modern history? Because this was no longer just about Huawei. This was about whether the world's second largest economy had managed to continue advancing despite years of coordinated technological pressure from the United States and its allies. And if that was true, the consequences could reach far beyond smartphones. The Mate 60 Pro quickly became more than a product launch. It became a symbol, a signal that the global technology war between China and the United States had entered a completely new phase. A phase where the world could no longer assume China would simply stop progressing because access had been restricted. And perhaps the most unsettling part for many Western officials was this: nobody saw it coming. To understand why the Mate 60 Pro shocked so many people, you first have to understand one thing about the semiconductor industry. Modern chips are not simply built, they are printed. Inside semiconductor factories, engineers use machines called lithography systems to carve microscopic circuits onto silicon wafers. These circuits are unbelievably small, thousands of times thinner than a human hair. Entire networks of transistors are compressed into an area smaller than a fingernail. And the smaller those circuits become, the more powerful and energy efficient the chip becomes. That is why the race to manufacture smaller chips has become one of the most important technological competitions in the world. At the center of that race is one machine that many people outside the industry had never even heard of until recently: the EUV lithography machine. EUV stands for extreme ultraviolet, and these systems are considered some of the most advanced manufacturing machines ever created. They are so difficult to build that only one company on Earth can produce them at scale: ASML in the Netherlands. These machines are enormous, incredibly expensive, and packed with highly specialized technology from multiple countries. Some experts have even described them as more complex than military fighter jets. The reason EUV matters so much is because it allows manufacturers to print extremely tiny circuits with extraordinary precision. Using incredibly short wavelengths of light, these machines can create microscopic patterns that older systems struggle to produce cleanly. This is the technology that helped companies like TSMC and Samsung Electronics push toward advanced chips used in high-end smartphones, AI systems, and modern computing hardware. And this is exactly where China ran into a wall. As semiconductor tensions escalated between Washington and Beijing, the United States pressured allies to restrict China's access to advanced chip-making technology. One of the most important restrictions involved EUV machines. China was effectively cut off from buying them. For many analysts, that single restriction was supposed to slow China's semiconductor ambitions for years. The assumption was simple: without EUV, China would struggle to manufacture truly advanced chips competitively. Instead, China was left using older generation machines called DUV systems, short for deep ultraviolet. Compared to EUV, DUV technology was viewed as older and less capable for cutting-edge manufacturing. It could still produce chips, but once engineers tried pushing toward extremely tiny nodes, the process became far more difficult. One way to understand the difference is to imagine trying to draw extremely thin lines on paper. EUV is like using an ultra-precise technical pen designed for microscopic detail. DUV is more like using a thicker marker. You can still try to create tiny shapes with it, but the process becomes harder, messier, and far less efficient as the designs shrink. That is why many experts believed China had reached a technological dead end. Not because advanced chips were theoretically impossible without EUV, but because doing it with DUV alone would become incredibly difficult, expensive, and inefficient. But SMIC reportedly attempted something that many people thought was unrealistic. Instead of relying on one clean printing process, engineers used a workaround technique known as multi-patterning. The concept sounds simple on paper. If one pass of the machine cannot create patterns small enough, engineers repeat the process multiple times. The wafer is printed again and again in carefully aligned layers until the final structures become much smaller than what the machine could normally achieve in a single pass. But in reality, this process is extremely complicated. Every additional step increases the chance of defects. Tiny alignment mistakes can ruin entire chips. Manufacturing becomes slower, more expensive, and much harder to scale efficiently. It is essentially engineers forcing older tools to perform beyond what many thought was realistically possible. And that is why the reports surrounding the Kirin 9000S created such intense reactions inside the semiconductor world. Because if SMIC truly managed to approach 7nm level production using advanced DUV multi-patterning techniques, then one of the biggest assumptions behind the technology sanctions suddenly looked weaker than many expected. For years, the global belief had been straightforward. No EUV meant no advanced Chinese chips. But now, China appeared to be proving something very different. Even without access to the industry's most advanced machines, progress was still happening. Maybe slower, maybe less efficient, maybe far more expensive, but not stopped. And in a technological rivalry this important, that distinction changes everything. When people talk about the semiconductor industry, they usually focus on the machines, the billion-dollar factories, the lithography systems, the clean rooms filled with advanced equipment. But behind every advanced chip is something even more important than the hardware itself: people. Because in the semiconductor industry, knowledge is one of the most valuable resources on Earth. And unlike physical machines, knowledge is much harder to block with sanctions. For years, much of the global conversation around China's chip industry focused on restrictions. Could China still buy advanced manufacturing equipment? Could Chinese companies access critical semiconductor tools? Could the country continue importing cutting-edge technology from abroad? But while the world focused on hardware restrictions, another battle was happening quietly behind the scenes: a global war for talent. Building advanced semiconductors is one of the hardest engineering challenges in modern industry. It requires deep expertise across physics, chemistry, materials science, manufacturing, software, and precision engineering. Even countries with enormous resources cannot instantly build an advanced chip industry from scratch. The learning process takes decades. Experience matters enormously. Tiny improvements in manufacturing often come from years of trial, failure, adjustment, and accumulated technical knowledge. And China understood that very early. Long before Huawei's Mate 60 Pro became international news, Beijing had already begun pouring massive amounts of money into developing domestic semiconductor capabilities. One of the biggest efforts became known as the Big Fund, a massive state-backed investment strategy designed to strengthen China's chip industry over the long term. Billions of dollars were directed towards semiconductor companies, research labs, universities, fabrication plants, and technology development programs. The objective was not simply to purchase foreign technology. China wanted to build its own self-sustaining semiconductor ecosystem. But factories and money alone were not enough. China also needed experienced people. Over the years, reports began emerging about veteran semiconductor engineers relocating to China from places like Taiwan, South Korea, and the United States. Some of these individuals had spent years working inside the world's most advanced chip companies. One of the most discussed figures was Liang Mongsong, a highly experienced engineer who previously worked at TSMC and later at Samsung Electronics before eventually joining SMIC. Inside the semiconductor world, engineers like this are extremely valuable because advanced chip making depends heavily on practical manufacturing experience. Not secret formulas, but accumulated technical understanding. Knowing how to improve production yields, knowing how to reduce defects, knowing how to optimize difficult manufacturing processes. These are lessons often learned only after years inside highly advanced fabrication environments. And that became one of the biggest concerns for Western governments and industry leaders. Because even if China was denied access to certain machines, the country was still gaining something equally important: expertise. The semiconductor industry has one of the steepest learning curves in the modern economy. Progress does not happen instantly. It happens through iteration, experimentation, and years of engineering experience. Sometimes a single experienced engineer can help solve manufacturing problems that delay entire projects for months. That is why talent became such a strategic issue. China was not just investing in factories, it was investing in people. Universities expanded semiconductor programs. Research institutions received larger budgets. Domestic companies aggressively recruited engineers with international experience. The country began building a larger pipeline of scientists, researchers, and chip engineers capable of contributing to long-term technological development. And unlike physical equipment, human knowledge moves differently. Machines can be blocked at borders. Exports can be restricted. Supply chains can be disrupted. But expertise spreads through people, through engineers changing companies, through teams learning from each other, through research, experimentation, and accumulated industrial experience over time. This is one reason why the semiconductor conflict became far more complicated than many initially expected. Because once a country develops enough internal expertise, progress can continue even under pressure, slowly, inefficiently at times, but continuously. And in China's case, years of investment were beginning to create something far more valuable than short-term access to foreign technology. A growing domestic base of engineers and researchers capable of solving increasingly difficult problems on their own. That did not mean China suddenly surpassed the world's leading semiconductor companies overnight. The technological gap in many areas still remained significant. But the larger realization becoming harder to ignore was this: technology can be restricted, machines can be denied, but human knowledge is far more difficult to contain. At first glance, all of this may sound like a story about smartphones and semiconductor factories. But for governments around the world, especially in Washington, the real concern goes far beyond consumer electronics. Because advanced chips are no longer just components inside phones or laptops. They have become the foundation of modern technological power itself. In today's world, almost every major industry is becoming dependent on advanced computing. Artificial intelligence, cloud infrastructure, autonomous systems, advanced robotics, electric vehicles, military technology, supercomputers. The smaller and more efficient the chip becomes, the more powerful these systems can become as well. That is why advanced semiconductors are now viewed as strategic assets, not just commercial products. A modern AI system processing massive amounts of data requires enormous computing power. Self-driving technologies inside future electric vehicles depend on high-performance chips capable of making rapid decisions in real time. Data centers running machine learning systems consume huge numbers of advanced processors. Even industrial automation increasingly depends on compact, energy-efficient computing systems. And this is where the geopolitical anxiety surrounding China's semiconductor progress becomes much easier to understand. Because the global technology race is no longer simply about who builds the best smartphones. It is about who controls the technologies that may define the next industrial era. Over the past decade, countries around the world began realizing that semiconductors sit at the center of almost everything. A nation leading in advanced chips could gain enormous advantages across multiple industries simultaneously. Economic influence, technological leadership, military capability, artificial intelligence development, manufacturing power, all of it increasingly connects back to semiconductors. That is why even relatively small advances inside the chip industry can trigger massive international reactions. And there is another dimension to this that makes governments even more sensitive: military applications. Modern warfare is rapidly becoming more dependent on compact, high-performance computing systems. Advanced drones, surveillance systems, missile guidance platforms, electronic warfare equipment, and battlefield AI all rely heavily on increasingly powerful chips. The smaller and more energy efficient those processors become, the more advanced military systems can become as well. A powerful chip no larger than a fingernail can now process enormous amounts of information in real time. It can help autonomous drones identify targets faster. It can improve satellite imaging systems. It can assist missile navigation and sensor fusion technologies. And unlike older computing hardware, advanced chips allow these capabilities to fit inside increasingly compact systems. That is one reason semiconductor technology has become deeply tied to national security discussions. For many Western officials, the concern is not simply whether China can produce advanced consumer electronics. The concern is whether China could eventually reduce its dependence on foreign semiconductor technology across critical strategic sectors. And this is why the semiconductor conflict escalated so dramatically in recent years, because whoever leads in advanced chips may gain enormous influence over the future direction of global technology itself. The country that dominates semiconductor development could potentially shape the next generation of AI infrastructure. This is also why semiconductors are often compared to oil in the 20th century. Not because chips and oil are physically similar, but because both became foundational resources powering entire economic systems. Countries that controlled access gained enormous geopolitical leverage. And now, advanced semiconductors are beginning to occupy a similar role inside the digital economy. This is why China's progress created such intense reactions internationally. Because for years, many Western policymakers believed slowing China's access to advanced chips would also slow its broader technological rise. But if China continues developing domestic semiconductor capabilities despite those restrictions, then the long-term global balance of technological power may become far more competitive than many originally expected. And that possibility carries implications far beyond the smartphone industry. Because beneath all the headlines about Huawei, sanctions, and chip factories, a much larger question is quietly emerging. Who will lead the next technological revolution?